Hi everyone, now we are at Integral Calculus, lecture number 12. So in this lecture we are going to discuss about applications of triple integrals. So there are so many applications, among them a few we are going to discuss. Okay, so let's start. First application, application number 1, volume of a solid. Okay, so triple integration over S dx dy dz, this gives volume of the solid S. So this is a solid S because it is a triple integration. The region of integration is a solid. For such solid S, it gives the value. This is a general formula. That is, it gives the volume of the solid S in Cartesian coordinate system. Same thing only. So if you consider the cylindrical polar coordinate system, then Jacobian will comes extra. So what is Jacobian cylindrical polar coordinate system? R. So R into dr d theta dz. Same thing, volume of the solid S, where the solid S is a part of a cylinder indirectly, right? So that is, it gives the volume of the solid S in cylindrical polar coordinate system. Okay. Similarly for spherical polar coordinate system. So again, Jacobian is rho square sin pi, what we have seen already. So into d rho d theta d pi. Again, this is value of the solid S, where S is a portion of a sphere or a sphere. That is, it gives the volume of the solid S in spherical polar coordinate system. So how this general formula comes, let me explain from double integrals. Okay. So if Z is a surface, Z is equal to f of x comma y is a surface, just recall the applications of double integrals. So then, okay, double integration over a region R, Z into dx dy. What it gives? It gives the volume, right? Volume under the surface Z. Okay. So this is what we have seen in a double integration. So let us consider a rough diagram. So for example, let's take for finding the volume of a sphere. So what we have considered, for example, let us look at for hemisphere only. Okay, for a while. So I suppose to find the volume of this hemisphere. Okay, so assume this Z is equal to, so obviously x square, for example, if it is a radius 1, okay, 1, therefore what is Z? Square root over 1 minus x square minus y square, isn't it? So what is the region of integration? So this is the region of integration, right? So this is my R, so this will be the region of integration, right? Because the shadow of this surface will be this circular ring in the xy plane. Okay, so in this region we have to integrate. So therefore the required volume can be obtained by double integrals z into dx dy over the region R. So in this region only you have to integrate, and y varies horizontally and x varies in this direction. So corresponding limits we have to substitute for R, for the region R. Then how to evaluate this? Look at now. So same thing I want to modify. So once it gives the value, so this also gives the value, right? How I am modifying? So z is equals to, I can write integration dz, right? So that integration derivative get cancelled. So that instead of z I am replacing integration dz. So instead of this z I am replacing integration dz. Z is nothing but integration dz. So therefore integration dz. So therefore one more integral will come, so dx dy dz. But over the entire solid we have to integrate. So now in this, so once it gives the value, so therefore this right hand side integrals also will give the value. So this is a general formula for evaluating the volume of a solid. And here the integrand is z, but here the integrand is 1. So therefore evaluation of this integral becomes easy rather than evaluating this integral, because here the integrand is z is there. Particularly for this problem, what is z? Z is square root over 1 minus x square minus y square. So evaluation of such integrals becomes somewhat typical compared to this integral. So this is easy compared to this integral, and both will give the volume of the solid. Here volume under the surface, this is volume of the solid. Okay. Next, let us evaluate volume of some solids. So problem number 1. Find the volume of a solid sphere of radius r. So this already we have done by considering surface in double integration. Now in triple integration, we are not considering such surface, only dx, dy, dz. So consider a rough diagram of a sphere. Remember, we have to find the entire sphere volume, right? So let us consider this is our required sphere. So for this sphere, having the radius capital R, and this for this sphere we have to find the value. Okay, right? Consider this is x-axis, this is y-axis, and this is z-axis. Okay, and assume this is rho axis. This is rho, and this angle is pi. This is pi. Okay, and consider this is r axis. Okay, this is r axis, and its angle is theta. This angle is theta. Okay, so so three variables are over: rho, pi, and theta. Now let us find out value of the required sphere. So triple integration over S. Assume this solid is S. I am denoting with S. The entire solid is S. So triple integration over S, dx, dy, dz. Since this solid is a sphere, so therefore I am adopting spherical polar coordinate system to evaluate the integral easily. So therefore for that Jacobian will comes extra. What is the Jacobian? Rho square sin pi. Okay, rho square sin pi, and d rho, d theta, and d pi. Okay, over the solid. Yes. Next we are supposed to find the corresponding limits of the solid. So let me write here. So first radius of the sphere. What is the radius of the sphere? R. So 0 to capital R. So R is vary from 0 to capital R. Next theta. So theta is a base angle. So here in xy plane. So to generate complete sphere, this r axis need to be rotated around z axis completely. So therefore 0 to 2 pi, because complete sphere I wanted. Next one we want pi, right? Pi limits. So pi is an angle between rho axis and z axis. Since we want complete sphere again, so again pi varies from 0 to pi, 0 to 180 degrees, because complete sphere we want. Already we have seen such kind of limits in the last class. So why this again? Why this pi? Let me look at once again. So this is z axis. This is z axis, right? Now this is my r axis. Let's consider this is my r axis, like this. So this one. So this is my r axis. So r axis, rho axis, sorry, rho axis. So this rho will be spread with respect to z. So therefore it spreads like this. It spreads like this. Okay. So up to this xy plane, how much it's spreading? 90 degrees it's spreading. So hemisphere is already generated, right? One more hemisphere, again one more 90 degrees below towards bottom. So therefore total 180 degrees. Okay. So therefore rho is equal to 0 to r, right? Next theta is 0 to 2 pi, 0 to 2 pi, right? Next one, and pi is from 0 to pi. Since all the limits are independent, so you are allowed to do with respect to rho first or pi first or theta first, your wish. Okay, now let us evaluate the integral. So therefore rho square sin pi. So first with respect to rho, because I have written first rho limits, so sin pi. So let me write first d rho. So after this, next with respect to d theta. After this, next with respect to d pi. Okay, so now this will be double integration pi is from 0 to pi, right? And theta from 0 to 2 pi, double integration of this. And next evaluate with respect to rho. So rho cube by 3, rho cube by 3. And where rho is varying from where to where? 0 to capital R, 0 to capital R. And sin pi is left. So sin pi, and with respect to rho is over. Next with respect to theta is supposed to evaluate. Okay. So now after theta, now with respect to pi we supposed to evaluate. Okay. Now this will be, so pi, so integration, pi runs from where to where? 0 to pi, right? And theta from 0 to 2 pi, right? Now let us substitute back what we got here. So rho cube by 3 I will get, that I will write outside, and sin pi d theta will remains, right? So therefore rho cube by, so r cube by 3, r cube by 3, that I am writing completely outside, and here what is left? Sin pi is left, right? So sin pi d theta, after that with respect to pi. Now this will be r cube by 3, r cube by 3, with respect to theta, so that sin pi is constant, so theta limits directly, so 2 pi I am writing outside. So theta you will get, right? Theta limits 2 pi to 0, 2 pi minus 0, 2 pi outside. And what is left? Integration with respect to pi is left. Pi is from 0 to pi, and sin pi d pi. Okay. And what about this one now? So total 2 pi r cube by 3, isn't it? And sin pi is minus cos pi, where the limits are running from 0 to pi, right? Now substitute back. So 2 pi r cube by 3, r cube by 3, and cos pi is minus 1, minus of minus plus, and minus, right? Minus, and cos 0, 1, so minus 1. So finally we will get 2 here. So therefore overall, so 2 into 2, 4, so 4 by 3, 4 by 3 into pi r cube, pi r cube. So cubic units, because this is value. Okay. So this is the sphere value. Look at how we generated. So these calculations have become simple compared to double integration. And moreover, so without using the spherical polar coordinate system also you can do this integration. For that we need to generate the limits in terms of x, y, z. For example, look at this. So assume we are not adopted spherical polar coordinate system, then how to evaluate this integration? Okay. Right. So assume this is x, this is y, and this is z. Okay. Now x limits. So x should vary in this direction, and y should vary in this direction, z should vary vertically. Okay. First z limits I want. Okay, z is varying from where to where? From bottom to top. From starting here, look at starting here and ending here. Because enter sphere I want. Starting here, ending here. Because z varies vertically, right? So what is sphere equation? Sphere equation is x square plus y square plus z square is equals to 1. So from this, what is z plus or minus square root over 1 minus x square minus y square. Okay. So this plus or minus, so if you take plus, you will get this upper portion. So this one is this upper portion. This one is z is equals to plus, you have to take square root over 1 minus x square minus 1 y square. Why? Because in the upper portion z is positive. In the below portion z is negative, right? So therefore this one you have to consider. This surface will be z is equal to minus square root over, okay, minus square root over 1 minus x square minus y square. So therefore z is varying from where to where now? So therefore the corresponding limits for z is square root over 1 minus x square minus y square. Okay. So minus of this less than or equal to z less than or equal to square root over 1 minus x square minus y square. Okay, z limits are over. Next I want y limits. Okay. Now we need to consider in 2D now, xy plane. In the xy plane, you have to consider this portion. So this one. So this is actually this is a circle, right? So this circle present in xy plane. Look at, so in this circle, y starts from here and ends here. Y starts here, ends here. So therefore, so therefore, what is circle equation? Circle equation in uh, two-dimensional. So it is x square plus y square is equal to 1. Same thing only, x square plus y square plus z square is 1, but in xy plane z coordinate is absent, right? Substitute z is 0 here, so that you will get x square plus y square is equal to 1. So this is circle equation in 2D. Okay, now so in this y value, so y varies from where to where, plus or minus square root over 1 minus x square. So therefore lower one you take minus square root 1 minus x square, and upper one you take plus 1. So overall, what are the y limits? Minus square root over 1 minus x square and plus square root over 1 minus x square. These are y limits. Now look at z and y's are dependent variables. And lastly, let us calculate x limits. So x varies. Let us take that bottom of the sphere outside. So it is a circle kind of, it is a circle, right? So therefore this equation is x square plus y square is equal to 1. Okay, so for this region we need to find x and y limits. So as x varies horizontally, y varies horizontally from the graph, therefore already we have considered this one. So right, so y varies in this direction, so therefore starting from this curve ending to this curve. But what is this curve? Minus square root over 1 minus x square, because it is in where in this coordinate, right, xz coordinate, so negative side. So therefore it will be minus square root over 1 minus x square, because y is negative in this coordinate. In this coordinate y is negative, because if you extend this line you'll get negative y axis, right? Here negative y axis, look at here, this is negative y axis, right? But lower bound is having here only, so therefore y is negative in this coordinate. That's why I am writing here minus, right? And upper bound will be here. This is upper bound, right? So this is upper bound, but it lies in positive y axis side, therefore it is plus square root over 1 minus x square. And corresponding x limits I want, so x should be negative x axis, so this is negative x axis. So starting from negative x axis to positive x axis, therefore, and since it's the radius of 1, so therefore the limits will be from where to where, minus 1 to plus 1. Okay, limits are minus 1 to plus 1. So under these limits you can evaluate. So this is x limit and this is y limit. Look at the limits itself are somewhat typical one, so that's why we are adopting the concept of spherical polar coordinate system. So take these three limits, and try to evaluate the integral, triple integration. There also will get same 4 by 3 pi r cube only, but evolution becomes somewhat typical, not so easy. Okay, but whereas you look at these calculations, it becomes so easy. That is the power of spherical polar coordinate system. Okay, consider this is second method. Okay, second method. We are evaluating in the Cartesian coordinate system or rectangular coordinate system. Now let's look at the second problem. Find the value of a box. So in the x direction it varies 0 to 2, in the y direction it varies 0 to 2, and in the z direction it varies 0 to 2. So the lengths are 2 units in all the three directions. Or simply we can code the same problem like this. Find the value of a cube. Why the word cube? Because lengths of all the sides are 2 units only, that's why it is a cube. The lengths of all sides are not equal, then it is a cuboid, right? So therefore it is a cube, so cube of side 2 units simply. So all the sides are equal to 2 units. Okay, now let's sketch roughly how it looks like. Consider a rough diagram for that. Right, so x-axis, this is y-axis, and this is z-axis. So x-axis, y-axis, and this is z-axis. Okay, now let's draw the cuboid. Start from here. Remember all the lengths are same. Okay, okay, and spread towards xy plane. So consider this cube, right? Now look at, so this first one, closed interval 0 to 2 means what? These are x limits. So starting from here 0 to 2 units. So this is 0 to 2. So therefore this point is 2. So this length is 2 units. 2 units. Okay. Next one, 0 to 2 for y. So this is for y, and this is for x, and this is for z limits. So y varies from 0 to 2. So y starting from here ending to this point. So therefore this length is 2 units. Starting from 0 ending to 2. Again z varies from 0 to 2. Therefore this length will be 2 units. Okay, and this length will be 2 units like this. So since it is a cube, right? So this length is equal to this length, right? Yes or no? So this length is equal to this length. Therefore this is also 2 units. And this length is equal to this length, but already this length is 2 units, therefore this length is also 2 units likewise, and this length is 2 units, therefore this length also 2 units. Indirectly we will get a cube, right? Now we are supposed to find volume of such cube, right? So by the concept of triple integration, so triple integration dx dy dz, dx dy dz over the solid S. Let's assume this solid is S. Okay, this solid is S, this entire solid. Now this will be, so triple integration, let us write all the limits. So x is varying from where to where? 0 to 2, and y is also varying from where to where? Y is also from 0 to 2, right? And z is also varying from 0 to 2, 0 to 2, right? So, so indirectly x is varying from 0 to 2 means what? X is starting from here, from the middle. Look at, x is starting from here 0, ending to this point means this plane. This plane is x is 2, right? So up to this. So what is this plane? X is 2. Therefore up to 2 it can vary. So x is equal to 2 it is likewise. Similarly y is 0 to 2 and z is 0 to 2. Okay. Now let us evaluate. So first with respect to x, next with respect to y, next with respect to z, like this. So first with respect to x, after that with respect to y, after that at the end with respect to z. So now this will be, so first with respect to x, therefore integration z is from 0 to 2, right? And y is also from 0 to 2, and x limits, dx means x. So x is varying from where to where? Integration dx is x, x is from 0 to 2. After that with respect to y, after that with respect to z. Okay, and this will be so integration z is from 0 to 2, and 2 I am writing completely outside. And next with respect to y, so with respect to y, simply y is varying from 0 to, after that with respect to z. So again substitute the limits, we will get 2 into 2 4, integration dz is z, again z limits are from 0 to 2. So overall 4 to the 8. So 8 cubic units. 8 cubic units. So this is about volume of the cube or this box. Similarly, next problem number 3. Find the volume of a box. X is varying from 0 to 1 and y is varying from 0 to 2 and z is varying from 0 to 3. Therefore, different limits, therefore it must be a cuboid. Or other way of asking the question is, find the volume of a cuboid of length 1 unit, breadth 2 units and height is 3 units. Look at height. Z axis varies vertically, that's why it is a height, and this is a breadth, and this is a length. So L, B, H, like this. Okay. Now look at, by the concept of triple integration only we have to evaluate. Okay. So let's look at the rough diagram for that. Right now, so okay. Right. So consider this is x-axis and this is y-axis and this is z-axis, right? So x is varying from where to where? 0 to 1. Therefore, so this length will be 2 units. Sorry, 1 unit, right? This length is 1 unit. So this is 1 unit, and y length 0 to 2 units. So therefore this length is 2 units from here to here. So this is 2 units. So this length is equal to this length, therefore it is also 2 units likewise. Okay. Next, z length is 0 to 4. Z is varying from 0 to 3. So this is 3 units. Okay. Remember, we are assuming the box is having one corner as a origin. Okay, one corner I am assuming origin. Then this diagram is correct. That's why I am drawing a rough diagram for this. Okay, now let's find out volume of such cuboid. So dx, dy, dz, dx, dy, dz. Now let us apply x, y, z limits. So z is varying from where to where? 0 to 3, right? And y is varying from 0 to 2, and x is varying from 0 to 1. So since I wrote in first z, therefore first with respect to z, after that with respect to y, right? After that with respect to x dx, right? Now let us evaluate one by one. So first with respect to z, therefore x is from 0 to 1 and y is from 0 to 2. So y is from 0 to 2. So integration dz is just z, and z limits are 0 to 3. So after z with respect to y we supposed to evaluate. So after y with respect to x we supposed to evaluate. So into dx. Okay. Now let us evaluate this one. So therefore after substitution of limits 3 will come. So 3 I am writing completely outside because it is a constant. Next with respect to y I supposed to evaluate, but y limits are from 0 to 2. And after that with respect to x is from 0 to 1. Right? After this I supposed to evaluate with respect to x. After this with respect to x. Right? Next this is so 3 into single integration 0 to 1 and integration dy is just y, and y limits are from 0 to 2 into dx. After that with respect to x we supposed to evaluate. So after substitution of limit you will get 3 into 2 6 integration 0 to 1 and dx is left. So therefore overall you will get 6 cubic units. Okay. How the limits will take place, look at once again. So since z varies vertically, therefore starting from xy plane, so starting from 0, because look at z varies from 0 to 3, so lower bound is 0, z value 0 in xy plane only, right? So z value 0 in xy plane or z is 0, whatever. Okay, so therefore starting from xy plane, so 0 to upper bound is 3, so in this direction over. Next come to the x and y limits. If you come to the x and y limit, that means you are in 2D. So now you need to consider this portion. So this portion you have to consider now in xy plane, right? In the xy plane, so x is varying in this direction and y is varying in this direction. So therefore y limits are, so therefore this strip is 2, right? This line is a plane is y is 2. So therefore starting from 0 ending to 2. Therefore y is varying from 0 to 2 and x limits are, so starting from here ending to here, right? So x is varying starting here and ending here. Therefore x limits are 0 to 1 likewise. So likewise you can proceed the limits. Okay. Next go to problem number 4. Find the volume of a cylinder x square plus y square is equal to 1 bounded below by z is 0 and bounded above by z is 3. So since here the cylinder is x square plus y square is equal to 1, that means it is having central axis is z axis. Okay, so let us draw the rough one. Okay, x axis, y axis and z axis. So let us consider this is x axis and this is y axis and this is z axis. Okay, let us extend this in the negative side y axis, right? Now the cylinder is, so this is the cylinder. Okay, look at for the cylinder, z axis is the central axis. Okay, so this is the cylinder and this cylinder bounded above by z is 3. Therefore this plane is, so this plane is bound z is 3. So this plane, so this is z is 3, z is equal to 3. Okay, and this one is obviously z is 0, xy plane means z is 0. So therefore bounded below by z is 0, that means it's starting from xy plane, bounded above by z is equal to 3, plane. So now this is a required cylinder. This is a given cylinder. X square plus y square is equals to 1. Now we're supposed to find value of this figure. That means, so this one, value of this entire thing we need to compute. So this value we supposed to find out. Okay. Now by using triple integration. So triple integration dx, dy, dz. Since the solid of integration is a cylinder, therefore I am adopting the concept of cylindrical polar coordinate system. So triple integration, right, over S, assume this solid S. Okay. Now, so in cylindrical, what is Jacobian? Jacobian is R, right? R, dr, d theta, and dz. Okay. In cylindrical polar coordinate system, the Cartesian coordinate x comma y comma z are rectangular coordinate. This one is transformed to r comma theta comma z in cylindrical polar coordinate system. Under the transformation, x is equal to r cos theta, y is equal to r sin theta, z is equal to z. Okay. So here we need to generate the limits next, right? Now look at, for this cylinder, r varies from where to where? Radius. So radius of the cylinder is 0 to 1, because the cylinder equation is x square plus y square is equal to 1. Next one, theta limits. So what is the theta here? Theta is nothing but angle between r axis to x axis, positive x axis. So this is theta, angle between r axis to positive x axis. So how much it need to vary? So the cylinder present around z axis, therefore it need to be rotated around z axis. So complete rotation should be required, therefore 0 to 2 pi. 0 to 2 pi. Next limit and next variable is z. So z is varying from where to where? Vertically, right? So starting from z is 0 and ending to z is equal to 3. That's it. So first with respect to r, therefore r into dr. So after that, with respect to theta, because I have written theta limits next. After that, we need to proceed with respect to z. Okay. Now let us evaluate this. So since first with respect to r, so z is varying from 0 to 3, right? And theta is varying from 0 to 2 pi, right? And r square by 2, r into dr, r square by 2, and r limits are from where to where? 0 to 1. So after that with respect to theta, and after that with respect to z. Okay. So theta, after that with respect to z. So therefore, so integration z is from 0 to 3, z is from 0 to 3, and theta, so let us substitute the value for r, so 1 by 2 you will get. Next with respect to theta, so d theta is theta, and theta limits from where to where? 0 to 2 pi. After that with respect to z, dz. So now this will be, so again 2 pi by 2 I will get, 2 pi by 2, and integration 0 to 3 dz, right? So this will be 2 pi by 2, 2 pi by 2, and z varies from 0 to 3. Integration dz is z. So finally, so 3 pi, 2 to cancel out 3 pi. So 3 pi cubic units. Okay, so this is about volume of this required solid. And same thing we have done by using double integration also. Once you look at and you try to understand the difference between finding the value by using double integration and triple integration. So that thing is very, very important. Okay. Next one, problem number 5. Let S be a solid inside both the cone z is equal to x square plus y square and the sphere of radius 1. Then find the value of S. If you look at the graph, so this is a graph. So this will be the required solid, and the same problem we have seen in a spherical polar coordinate lecture, right? So here what we are having is, this is my rho axis, right? So let us extend this, right? This is z axis and this will be rho axis, right, till this point. So angle between rho, assume this is rho axis, and angle between rho and z will be what? It will be pi. So this is pi. This angle is pi. So now this rho axis spreads around z axis, right? So this is z axis now. So now this is rho axis. It's spreading like this in all the directions. So if it spreads 45, if it spreads 90 degrees, I will get a hemisphere, right? But 90 degrees, 45 degrees I'm spreading from here to here, so that this kind of cone will be generated. Look at this is a cone. That's why pi is equal to pi by 4. In the last class I did, pi is equal to pi by 4 represents, it is not an angle, it represents a cone in where in spherical polar coordinate system. Okay, spherical polar coordinate system. The same thing I have done in the last lecture. Coordinate system. Okay, so pi is pi by 4. Starting from where? So starting from z axis, therefore pi is starting from 0 ending to pi by 4 to generate such kind of solid. So therefore directly I am proceeding. So therefore triple integration dx dy dz. So this is general formula, dx dy dz over r. Since the region or the solid of integration is a part of sphere, therefore I am adopting the concept of spherical polar coordinate system. So this is my solid S. This is my solid S. Okay. And in spherical polar coordinate system, what is Jacobian? Jacobian will be rho square sine pi. Rho square sine pi d rho d theta and d pi. Okay. Now let us substitute all the limits. So therefore triple integration. Yeah. First let me write here the limits. What are the limits first? So first rho limits. Rho is nothing but radius of the sphere, right? 3D radius. So since sphere radius is 1, therefore rho varies from 0 to 1. Okay. Next one theta. So theta is a base angle. So since this cone is generating around z axis, around z, therefore theta should rotate around z. So therefore complete angle I want. So therefore 0 to 2 pi. The r axis should rotate completely around z axis. Completely means 360 degrees. Next one, pi, right? So since it is a cone, so pi must be 0 to pi by 4. 45 degrees it has to move from starting from 0, so that this cone will be generated. If you move more, pi by 4 plus something else, some 10 degrees, again cone will get, but not this cone, somewhat spreads. It gives little more value. Okay, so therefore pi value varies from 0 to pi by 4 according to this problem. So therefore let us substitute the limits. So pi varies from 0 to pi by 4. Since all are independent limits, so order of integration does not matter. Okay, and theta limits from where to where? 0 to 2 pi. Okay, 0 to 2 pi. And the radius rho varying from where to where? 0 to 1. Or first with respect to rho also you can do your wish. Okay, and what is the integrand? Integrand is rho square sine pi. Rho square sine pi. So first with respect to pi. Okay, so after that, which limits is applied? Theta. So therefore next with respect to theta, right? After that with respect to rho. Once again I am telling, since all the limits are independent limits, so order of integration does not matter. First with respect to rho you can evaluate, or first with respect to theta you can evaluate, or first with respect to pi you can evaluate. And one more, pi is equal to pi by 4, I have given the proof in the last lecture, that is the lecture related to this spherical polar coordinate system. There I proved z is equal to this, z is equal to square root over x square plus y square means pi is equal to pi by 4. This I proved in the last lecture. Let's look at for the reference. Okay. Yeah, let us evaluate this. So rho is from 0 to 1, right? And theta is varying from 0 to 2 pi base angle. And with respect to pi first, so rho square as it is, because integration with respect to pi, so integration sine pi will be minus cos pi, and where the limits runs from 0 to pi by 4, 0 to pi by 4. So after that with respect to theta, right? And after that with respect to rho, now this will be, so rho is from 0 to 1, right? And theta from 0 to 2 pi. Now rho square, so minus rho square I am writing, so minus I am writing outside. So cos pi limits, so cos pi by 4 1 by root 2, and cos 0 minus 1. cos 0 1, but since it is lower bound, therefore minus. And after that, with respect to theta, I need to evaluate, and after that with respect to rho. Okay, so let us proceed in next slide. So rho is from 0 to 1, right? So rho is running from 0 to 1, and theta is running from 0 to 2 pi, right? And what is the integrand? So minus rho square into 1 by root 2 minus 1, right? So that constant I want to write outside. So therefore 1 minus 1 by root 2. So including minus, so 1 minus 1 by root 2 I am writing completely outside. Okay, and inside rho square will be left. Okay, rho square into d theta first. So rho square will become constant now. Okay, after this with respect to rho I need to evaluate. So this will be, so 1 minus 1 by root 2, right? And evaluate with respect to theta now. So only theta will come. So 2 pi minus 0. So 2 pi I am writing completely outside. Next integration, rho from 0 to 1, rho square into d rho. Okay, and this will be 1 minus 1 upon root 2, right, into 2 pi into 2 pi, and rho square, so rho power 3 by 3, rho power 3 by 3, and where the limits are from 0 to 1, rho is from 0 to rho is equal to 1. So now this will be, so 1 by 3, so 2 pi by 3. Okay, so 2 pi by 3, 1 minus 1 by root 2. Okay, so cubic units. So this is the volume of that required solid. Okay, next problem number 6 and 7. Look at, roughly I will give the idea about this. Look at now, find the volume of a triangular prism with ends given by the planes y0. Y0 means what? XZ plane. So this is XZ plane because this is Z axis, this is X axis, right? So in this plane, y coordinate is absent. That's why this is y0. Okay, so let me write that. So this will be y0. So this is y0. Next, what is given? Y is equal to 2. Y is equal to 2, right? So this will be y is 2. Look at, since why this is y is equal to, because this is y axis, so therefore passing through the point 2, therefore this is y is equal to 2. Y is equal to 2. So therefore y varies in this direction. So starting from 0, so this is y0, right? This is y0 because intersection portion we are taking. Actually this entire plane is y0, but we are considering intersection one. So this will be y0, y varying from 0 to 2, y is over. Next, x is varying. So x is 0. X is 0 means what? YZ plane. YZ. So this is YZ plane. So this is x is 0. Right? Therefore, this will be, yeah. So right. So this will be y0. Sorry, x is 0. Okay. So this is x is equal to 0. Right? Next one, z is 0. Z is 0 means what? XY plane. So this is, in this z is 0. That means, so this will be z is 0. So this will be z is 0. Okay. So this one, right? From here to here. So this is z is 0. This plane is z is 0. Right? Next one, look at the plane. The plane x plus 4z is equal to 4. If you divide with 4 both sides, you will get x by 4, right? Plus z is equal to 1. So now this is a plane intersect x-axis at 4 comma 0 comma 0, right? And intersect z-axis at 0 comma 0 comma 1. So z by 1, right? So therefore 0 comma 0 comma 1 means this point is 0 comma 0 comma 1. Look at this point is 0 comma 0 comma 1, right? And next 4 comma 0 comma 0 means, so this point is 4 comma 0 comma 0. This is 4 comma 0 comma 0. So therefore now the plane passing through these 2 points, cutting x and z axis at these 2 points, therefore so this is the plane. So this one, so this red color one, so this red color one will be the that plane. So this red color one will be the, what is that? X plus 4z is equal to 4. Clear? Now let's look at the volume of such solid, such prism. So let us write the prism is, so dx dy dz, dx dy dz, right? And this will be, let me write, I will write the limits and you proceed. First let us write z limits. Z should vary vertically, right? So z should vary in vertical direction, so in this direction. So therefore starting from xy plane, right? So therefore z is 0, ending to this red color plane, look at, and this red color plane is x plus 4z is equal to 4, ending to this plane, right? So therefore from this, what is z value? So z value is equal to 4 minus x divided by 4, isn't it, z value? So therefore upper bound will be z is equal to 4 minus x by 4 over. Next come to the xy plane. Let us write y limits. Y should vary horizontally according to the figure, according to the diagram. So y should vary horizontally, starting from where y is 0, starting from this strip. Look at, starting from this plane y and ending to this plane, but this plane is y is equal to 2, right? So therefore starting from 0 to ending to 2. Therefore now y limits are 0 to 2, isn't it? Next, x limits we are supposed to supply. And what about x limits? X should vary in this direction, right? So x should vary from here to here. So starting from where? Starting from this plane, right? X is 0. This is starting from x is 0, ending to, what is this? This is 4, right? This line, this plane intersecting x-axis at 4. Therefore maximum value is 4. So therefore x starting from 0, ending to 4. Therefore x limits 0 to 4. That's it. So since z is dependent, therefore first with respect to z you have to do, and remaining two variables x and y are independent, and that doesn't matter. You can do next dx or dy, after that dy. Evaluate this. Okay, take it exercise. Okay, next look at problem number 7. Find the volume bounded by the cylinder x square plus y square is equal to 4. That means central axis z axis having the radius 2 units of the cylinder. Look at, this is a cylinder having central axis z axis, right? And the plane y plus z is equal to 4. Y plus z is equal to 4 means what? So let me write this one. Let us divide with 4. So what will get? Y by 4 plus z by 4 is equal to 1. That means this plane intersect y axis at 0 comma 4 comma 0, and the same plane intersect z axis at 0 comma 0 comma 4. So these 2 points we have to mark. So therefore on y, so this is y axis, therefore this point will be 0 comma 4 comma 0, 0 comma 4 comma 0. Indirectly this length is 4 units, this y length is 4 units, and this point intersected z axis at what point? 0 comma 0 comma 4, 0 comma 0 comma 4, that point. So therefore this vertical length is also 4 units. So this plane, so this one is a plane. So let me look at this. So this is a plane. So this is the plane which is intersect x-axis, y-axis at 0 comma 4 comma 0, and z-axis at 0 comma 0 comma 4. So this is a plane, that one. Okay, and this plane will be y plus z is equal to 4. Y plus z is equal to 4, this plane, right? And what is the cylinder? X square plus y square is equal to 4, therefore having radius 2 units. Okay, and next one more, and z is 0. Z is 0 means what? Xy plane. So therefore above xy plane we have to consider. Above xy plane, or simply z is 0. Z is 0 means z coordinate will be absent. That means that is xy plane only. Okay, so therefore volume of such solid triple integration dx dy dz. But since the solid of integration is a part of cylindrical cylinder, so therefore we may apply cylindrical polar coordinate system to evaluate the integral easily. So for cylindrical polar coordinate system, so then what is Jacobian? Jacobian will be rho, right? Rho into, sorry, r, right? R into dr d theta dz. So for this, now the variable is r theta z, right? So let me write here the r limits. So r is varying from where to where? Radius. So radius is from 0 to 2, because cylinder radius is 2 units. R is over. Next theta I want. So theta varying from where to where? So theta is nothing but base angle, right? So it is around z axis, therefore completely it has to move. So 0 to 2 pi. So theta also over. And next what is left? Z is left. But look at, z is varying from 0, right? Xy plane means it is 0. So starting from 0, what will be upper bound? Upper bound will be this one. It's not completely z is 4. If I take z is equal to 4, that means this kind of uh, cylinder you are considering. So this kind of cylinder you are considering. If you take z is equal to 4, because this plane is 4, right? This is 4, z is 4, this is z is equal to 4. This point is 4, right? Look at here. So this point is 4, that's why this plane is z is 4. So that means we are considering full cylinder. So we should not take z is 4 up to 4. So we need to consider this plane now, upper bound. Upper bound will be this plane. So what is z value from here? So from here, z value will be 4 minus y. But since we are changing the variable x comma y comma z to r comma theta comma z, therefore this variable also we need to modify. So therefore 4 minus, what is y? In the cylindrical power coordinate system, y is equal to x is equal to r cos theta, y is equal to r sin theta. Right? So look at, now we are changed it completely. Therefore z limits upper bound is 4 minus r sin theta. So these are the limits. With these limits you can proceed this integration. So you're supposed to get the answer is 16 pi cubic units. This you will get answer. Check once. And here z is dependent, right? So first with respect to z you have to evaluate, and remaining two variables are independent. R and theta are independent. So first with respect to theta you can evaluate, second with respect to theta you can evaluate, or with respect to r you can evaluate, your wish. Next, application number 2. So total mass. If a density function is given to us, which deals about mass per unit volume, then triple integration of rho of x comma y comma z into dx dy dz over such solid t gives the total mass of that solid t. Okay, and similarly application number 3 gives center of gravity, which is x bar 1 over m triple integration x into density function dx dy dz, and y bar is equal to 1 over m triple integration over t y into density function, and z bar is 1 over m triple integration z into rho of x comma y comma z dx dy dz. So these three will give center of gravity, where m is total mass, what we discussed already in application number 2. So the coordinate x bar, y bar, z bar is said to be center of gravity of the mass m in the solid T. Look at, for example, this figure. So let's say this is y-axis and this is z-axis. So for this cube or cuboid, whatever, so consider this is a cube. So this point will be center of gravity. So midpoint of that solid. Okay, this gives the center of gravity. So this point we are going to evaluate now. So this is x bar, y bar, and z bar. So that point is center of gravity. X bar, y bar, and z bar. Let's have one problem related to this. Problem number 1. A cube of side 3 units is made of laminated material with the origin at one corner. And density of the material will be constant, where k belongs to real number system. Then find the center of gravity of that cube. So first let us look at its total mass. So this is the cube. So it is having 3 units of length. So this length is 3 units. So assume this is x-axis, this is y, and this is z. Okay, this is z-axis, right? And this length is 3 units, and this length is 3 units. It is having one corner at origin, right? So this is one corner, so this is origin. Okay, and this length is also 3 units. So all the lengths are equal, so that's why it is a cube. So first let us compute the total mass. So total mass is obtained by the triple integration over the solid T. Let's assume it is a solid T. So T and the density function into dx, dy, dz. Okay. So now what is the density function here? So density function is constant. So k into dx, dy, and dz. And corresponding limits, z is varying from where to where, since it is a cube, so 0 to 3, and y is also from 0 to 3 from the graph, and z is also from 0 to 3 from the graph. Z is also varying from 0 to, sorry, x, right? X is also varying from 0 to 3. Now let us compute this. So here k is a constant, will comes out. So integration first with respect to z you evaluate. So x is 0 to 3 and y is 0 to 3, Okay, first we have written z, so with respect to z you evaluate first, therefore integration dz is z. Okay, and z limits are 0 to 3. So after that with respect to y, okay, and after that with respect to x, okay, then this will be, yeah, what will get, so this is k is out and 3 is also out, 3k. So integration x is from 0 to 3, okay, and with respect to y, so z limits are 0 to 3, okay, and dx. So again one more 3 will comes out, so total 9k, and integration dx is x limits are 0 to 3, directly I'm evaluating, so total 27k. So this is total mass. Okay, next we are supposed to find the center of gravity. Okay, so the center of gravity will be, yeah, so x bar, y bar, and z bar. So this is our center of gravity. So let us find one by one. So first x bar. What is x bar? So 1 upon m, right? Triple integration density function into dx, x into, right? So here x is, so x into, so x into density function into dx dy dz, dx dy dz. Okay, so now this will be 1 over m, triple integration x into, what is density function? Density function is k into dx dy dz. Okay, so then, so 1 over m, that I will substitute at the end. Yeah, so triple integration, let us substitute all the values. First x limits, x is running from 0 to 3, right, and y is also running from 0 to 3, and z is running from 0 to 3, z is, right. So k is a constant, I am writing completely out. So x into dx, after that with respect to y, after that with respect to z. Therefore k over m, right. So integration z is from 0 to 3, and integration y is from 0 to 3, and with respect to x we are supposed to evaluate first, so x square by 2, and where x is running from 0 to 3. Okay, after this with respect to y, okay, after this with respect to z, is lost. Okay, so now this will be k over m, and integration z is from 0 to 3, okay, and y is from 0 to 3, right, and if you substitute the limits, 9 by 2, so 9 by 2 I am writing outside, so here dy, after that dz. Okay, so yeah, continuation here. Yeah, so next, so k over m, okay, 9 upon 2, z is from 0 to 3, right, integration dy, and integration dy is y, so y limits are 0 to 3, after that with respect to z. So again one more 3 will comes out, so k upon m, 9 3 is 27, 27 upon 2, next integration dz, so dz will be z, again z limits are 0 to 3. So finally what we got is k upon m, right, 27 upon 2 into 3. Okay, now let us replace, but what is total mass? Total mass will be 27k, that we computed already. So then plug in back, so what will get, so k upon, so m value is 27 into k, and 27 upon 2 into 3. So 27k will be cancelled out, so 3 by 2 will remain. So x bar will be, so therefore first coordinate of the center of mass is 3 by 2. Okay, so next one, y bar, so second coordinate of center of gravity, so 1 over m, right, triple integration y into density function into dx dy and dz. So here also you are supposed to get 3 by 2, try once. Okay, next z bar, What is z bar? Z bar is again 1 upon m triple integration, right? Z into density function into dx dy dz. Okay, again this one you're supposed to get 3 by 2. Try once. Okay, so therefore overall the center of gravity, the center of gravity, okay, gravity of the cube is x bar, y bar, z bar, which is, what is this, 3 by 2 comma 3 by 2 comma 3 by 2. Okay, so this is about center of gravity. So here I have taken constant density function. You can take variable density function also, and the procedure is same. Let us take few Excel problems, and with this I will stop.